So I like to work some exercises right now. I think I'll take a few of these from the book maybe. This is, I think, number 12. This is from section 7.2. It's like around page 201, I think, in the current textbook. So what we want to do, we want to let A and B be elements of a group G. We want to show that, what does it say? A, B to the n, A inverse equals A, B, A inverse. Oh, and n. Okay, I miswrote it. Let me rewrite this. It should be to the nth power, all of this. So A, B, A inverse. All of that raised to the nth power. This is for any integer n. So positive integers, negative integers, and 0. Let's do it for all three. Let's actually do it for all three. Most of the time I just do it for the positive because that's the easy case. Proof. So let's take a positive integer n. What's A, B, A inverse to the n power mean? So I dropped my stars, I'm just putting them next to each other. This actually means what? A, B, A inverse, A, B, A inverse, A, B, A inverse. How many copies? N copies. So what we're going to do, we're going to basically put the A inverses together. So you're going to have A inverse A. You're going to have A inverse A here. You're going to have A inverse A. It's going to happen many times. You're going to end up with A, B, then an identity, and B, and then A inverse A is going to give you identity, and so on and so forth. They're going to have an identity, and then a B, and then an A inverse. And they're going to have from here to here, how many B's are going to have with the E's? N minus 1 copies. Right, we took an A in the front and an A inverse in the end. So now we have N minus 1 copies. So. No, I'm sorry, the B's, there's still N B's. That's not going to change. What am I talking about? Still N B's, that hasn't changed. Okay, they're going to be N B's, they're going to be N minus 1 E's. So let me just write it that way. No. N N B's. I believe N minus 1. Yeah. Made this right. So there'll be N minus 1 copies of E and N copies of B here. Okay, now the E's, when you multiply the E's by the B's, you're going to get a bunch of B's. You're going to get A and then a bunch of B's and A inverse, but there's still N copies of B. In other words, we can call that A, B to the N, A inverse. That's what we wanted to get, right? So that does it for the positive integer case. Let's take a negative integer case. Well, let's do the 0 case. That's the easy one, right? A, B, A inverse to the 0 power. That's understood to be the identity, which is the same as A inverse, right? Which is the same as A times the identity. times A inverse, right? Which is the same as A B to the 0 times A inverse. And that's it, right? Here you had the 0 power, here you had the 0 power. Okay, that's the case for when you have a 0. Now let's talk about like a negative n. Finally, that'll be the hard one, probably. I have ABA inverse, and I have a minus n power here. There are a few ways you can think about this. One of the ways you can think about this is simply, okay, A, B, A inverse, inverse to the n power. Now, the easy way to do this is to apply the negative 1. So if you do that, you get A to the negative 1 to the negative 1. Remember the reverse order. B, and then a inverse, and then A, and then a inverse, and all to the n power. So you get what? A, B inverse, A inverse. And now n is actually a positive integer, so you can apply basically the part when you have the positive integer to this. You can just say this is A, B to the negative 1 to the n, A inverse. That was by, this from here to here is by using the first part, because n's a positive integer, by using the positive integer case. And then we can just rename this A, B to the minus n, A to the negative 1. And there you have it. Right here you had a minus n exponent, here you have your minus n exponent. So it all works out nice. Okay, so that was like a number 12. Now let's do number 24. This is from the same section, section 7.2. If AB squared equals A squared B squared for every pair of elements, A and B, in the group, then the group is abelian. Okay, so we're going to assume, we're going to assume AB squared equals A squared B squared. So suppose AB quantity squared equals A squared B squared for all A and B in the group. Now, I'm going to copy down what that means. On the left side, what does it mean AB squared? That means AB, right, times AB. And on the right side, that means AA times BB. This is for all A and B in the group G. So what we're going to do now, we're going to do left cancellation by A and right cancellation by B. By left cancellation on A and right cancellation on B. So left cancellation on A, I'm taking this A, say I'm going to cancel those. And right cancellation on B, I'm going to take this B and this B and cancel those. What do we end up getting? We get that BA equals AB for all A and B in the group G. So if AB equals B, or if BA equals AB for all elements, A and B, therefore, the group is abelian. I write my abelian with a capital A rather than a lowercase a. There we go. End of proof. This is going to be number 27. Section 7.2. This one's an interesting one. Show if every non-identity element of G has order 2, then G is abelian. Lowercase a, let me put the uppercase a. Okay, let's begin the proof by assuming every non-zero element of G has order 2. So suppose every non-identity element has order 2. So let's take an arbitrary element of the group G that's not zero, not the identity. Let A be an element of G with A not the identity. So we're taking a non-identity element. Then that means the order of A is equal to 2. In other words, A squared equals the identity, right? In other words, that is AA equals the identity. Now what I'm going to do, I'm going to multiply on the left each side by A inverse. I'm going to do A inverse AA equals A inverse E. So that's going to be equivalent to the identity times A equals A inverse. And that's going to be equivalent to A equals A inverse. So what we've shown is every non-identity element is its own inverse, right? A equals A inverse. But we also know the identity is its own inverse as well, right? So note also the identity's inverse is the identity. So therefore, every element is its own inverse in this group. Therefore, X equals X inverse for every X in this group. Means every element is its own inverse. So the identity is, and every other element is. Okay, so we want to show this is abelian. Let's take two arbitrary elements. What do we want to call them? I've used already A. I used X. Okay, we'll just say, let's take X and Y. We want to show X and Y commute. So let's take an arbitrary and X and arbitrary Y. Let me get a different color, orange. I like orange. Let X and Y be in G. So they're arbitrary elements. Then we know X times Y is in G, right? It's closed under the operation, the star operation. But also we know that XY is its own inverse. So XY is going to be XY inverse. And remember that the inverse of XY is going to be Y inverse X inverse. So basically the star product in reverse order. The star product in reverse. No, how should I say this? The star product of the inverse is in reversed order. Okay. What's another name for Y inverse? Another name for Y inverse is Y. Another name for X inverse is X because it's its own inverse, right? So what do we got? We got XY equals YX. That's it. Therefore, because every pair of elements commutes, therefore G is abelian. Capital A. I'm going with the capital A. Okay. Nice little problem. I like that one. Something else I can do in here real quick. I don't want to take any of the fun away from your homework or anything like that. That should be good enough right now, I think.